So what I'd like to do is to just kind of briefly introduce the topic, and then I would like to introduce the panelists, and then following the model that we've used for these sessions, each of the panelists will have 10 minutes to speak, and then we'll have a session of questions kind of at the table, and then we'll open it up for general questions. And I guess I would just follow on to Dave's comment. Energy efficiency in information and communication technology is a bit different than the other themes. One of the things that one could note almost immediately is that if you look at the energy budget globally, where the energy goes, the energy used for information and communication infrastructure, that is the network piece, is a small portion of the total. It's only a couple of percent. And so you might argue, why do we even need to worry about it? Now, the fact of the matter is, at the end of that network are wireless devices, and clearly in that space there's a larger component. But overall, not the 33% that transportation, et cetera, et cetera. At the same time, we are living in a world that is dramatically changing, and in everything that you and I do on a daily basis, that network is instrumental to what we do, whether it's business, whether it's entertainment, whether it's virtual travel potentially in the future. So increasingly, not only are we using that network to do our kind of daily tasks, but we're also looking for ways to use that network to avoid some of the other ways that we consume energy today, for example, again, in something like a virtual travel. So the net result, and you'll hear that from the panelists, is the demand on that network from a usage point of view, from bandwidth demand, raw bandwidth need, continues to go up exponentially. And as a result, to build out, to respond to that need, increase in capacity in the network is necessary. If we do that simply by building parallel networks, first and foremost, even if we do that, then we grow the amount of energy linearly. That's not allowed. Even more importantly, if we try to do that, we grow the costs linearly. That doesn't scale well. The whole reason that we have the ubiquitous global communication network that we have today is that people like those who are sitting on this panel have been able to dramatically reduce the cost per bit for transmission systems, for communication systems, in such a way that as the demand has continued to grow, and in the network that demand has grown roughly a factor of 100 every 10 years for the last 30 years, nevertheless, at a cost per bit, it's going down almost at the same rate as the demand is going up, so that the actual cost to build the next generation network can't go up with the bandwidth requirement. It actually stays flat or actually has to go down a bit. Now, the good news in that, from an energy point of view, is that in the network, that goal and that driver, which is keeping the cost down and basically reducing the cost per bit, which ultimately is the decision that the service providers will use to choose systems, is also driving the energy per bit down, just as a kind of fortuitous situation. So that's the good news. The bad news is that our ability to continue to drive in the long haul that continued increase in capacity is being challenged, and you'll hear some of that from one of our speakers. As importantly, as the cloud emerges, increasingly that computing in your home is going to data centers to be processed. That's good from an energy efficiency point of view. Much better to have consolidated computing than distributed computing over large areas. And as long as we can then also make the energy efficiency of that network sufficiently low, then that whole process is one that reduces that at least keeps the energy requirements without becoming totally out of hand as the demand goes up, and we know that the demand is going to go up. So that's one of the reasons that we included it, because in this economy, in this world we live in, being able to grow the capacity of the network without growing the energy requirement is absolutely critical. So with that bit of background, I'd like to introduce our panelists. And so first, To my left is Steve Alexander, who's Vice President and Chief Technology Officer for Ciena, and he will be giving a presentation transforming the network energy efficiency in the WAN, which is the Wide Area Network. Steve has more than 20 years of telecom experience. He's currently serving as Ciena's Senior Vice President and Chief Technology Officer. Prior to that, Steve was at MIT Lincoln Labs, where he did some of the very initial work in the space of optical networking and in driving the technologies for optical communications. He's won a number of awards for the work that he does. He's active in IEEE, and from my view, he has been a driving force in the evolution of optical networks from both the technical and the business point of view. Next is Mario Paniccia, who's an Intel Fellow and General Manager of Silicon Photonics Operations Organization within Intel. He will give a presentation, Silicon Photonics in the Data Centers. Mario joined Intel in 1995 as a lead researcher in developing a novel optical testing technology for probing transistor timing in microprocessors. And today, that optical testing technique is a standard in the industry. My perspective on Mario is that success was the kind of beginning of his quest to explore all that which optical technologies can bring to increase benefits, either from a performance, cost, or energy point of view, in applying and improving what we do in electronics, and we'll hear from him. Next is Ashok Krishnamoorthy, who is from Oracle Labs, and is Oracle's architect and chief technologist in photonics. Ashok has had a career in which he's been involved in the packaging and integration of photonic devices with silicon CMOS circuits, including electro-optic modulator silicon. So essentially, Ashok is trying to get electronics and optics together for a long, long time, is now the chief PI on a DARPA project, which is doing some very, very exciting work in applying optics to very short-range interconnect for very high-capacity needs inside of computing and switching. And you all know John Bowers. John Bowers is, of course, the director of the Institute for Energy Efficiency here at UCSB. He's also professor of electrical and computer engineering at UCSB, and his talk will be on low-power optical switching and silicon interconnects. John has been not only extremely active, but hugely productive in this area of optical communications, optical devices. He's been an entrepreneur, started several companies. He's received numerous international awards in recognition of the seminal work that he's done in this field and the impact that his work has had, most recently in the area of silicon photonics. So with that, let's start with Steve.
So Rod and John, thank you very much. It's a pleasure to be here and talk about the network piece. And as Rod said, I would argue that today the network probably matters more than it has in a decade, for the simple reason that it is the most networked society we've ever had. If you've seen the rise of the social networking, that's the fastest adopted technology really in history. And as we move to the cloud, how you get to the cloud, how you get to those resources in the cloud is the network, right? And so I think there's a case to be made for the quality and quantity of that connection, that bandwidth, that capacity that you get from the network determines your user experience today like more than it has in a decade or so. So it's actually a very good time to be in the networking space. There is some interesting things coming at us though. And I think if you paid attention to what people have been saying in terms of bandwidth demand, capacity demand, you've all seen these hockey stick curves. The piece of it that I particularly like is the sound bite, right? Which is, soon the amount of traffic carried in the mid-2000s. So what we're coming up to, right? Kind of middle 2010s and such. That will be so much greater than anything that was carried before. What we built back in the bubble days, the mid-2000s, that's going to be a rounding error. Okay, so you think about the network having to get 10 to 100 times bigger. you could kind of make an argument that says, well, that means most of the work's in front of us, right? The network, the capacity, all the things that we've deployed to date, that might be 10% of what needs to be actually deployed going forward. So a lot of work is in front of us on how this all has to play out. And when you factor that into some pretty fundamental limitations, some of them on the physics side, you know, we're up against getting close to Shannon's limit, how many bits we can stuff into a channel. We're up against just economic limits. If you look kind of globally, how much of the world global domestic product can be spent in ICT, it's something like 5 or 6%. There's far more important things to spend on, like food and housing and such. So the network can't get 10 or 100 times bigger, take up 10 or 100 times as much space, consume 10 or 100 times as much power, cost 10 or 100 times much. It's just impossible, right? So things have to change. And it turns out that we're kind of building what we would call WAN, Wide Area Network 3.0, right? Even if we don't really realize it. There's been effectively 3 of these large investment cycles, these waves, if you will, in the telecom infrastructure. For those folks who've been around it for a long time, they'll remember kind of WAN 1.0, PDH, Plesiocrates, digital hierarchy and such. What most people experienced was out at the edge of the network, what did you get? You got dial-up. You had a voice system, and you could put data over the top of it. And there was even a belief for a period of time that the data was a fad. Now, we all know that's not the case, but that was the first instance of where photonics was applied to networking. We had lasers, we could drive them at gigabit rates, and we could interconnect cities and towns over fiber, right? So truly a revolution. In '89, the world changed for us. Erbium fiber amplifier gets developed. And at the same time, we had another technology, SONET, or SDH, synchronous digital hierarchy, where we could time a lot of things, and we could send things over much greater distances, and we could have rings, and we could have automatic restoration and such. And a whole lot of money gets spent, right? You know, another, in this case, $80 billion roughly has been spent in the SONET SDH infrastructure swap out. But we're actually now into the 3rd phase of this, what we call WAN 3.0. And there's been a couple of kind of key developments. One has been, quite honestly, Ethernet, right? Everybody throws the Ethernet term around, but it is a fundamental shift for us in the networking space. It grew up through the datacom space, but a wonderful thing happened when we got to 10 gigabits. There was a data rate in the synchronous world of 10 gigabits. There was a data rate in the datacom world of 10 gigabit Ethernet. I could buy the same parts, build 2 different types of networks, great economy of scale occurs, and once those 2 worlds come together, they don't separate. And so we're now in the midst of this WAN 3.0. It's an Ethernet world. If you think about it, Ethernet accomplished something very important. It's global standard. We never had that before, right? We had originally national standards, and we went to regional standards. Now we have one big global standard called Ethernet. We also have one G.709 OTN. The combination of those things means we can build networking equipment, take it anywhere in the world. And Ethernet's unique in the sense that it is absolutely the same everywhere in the world, right? Our prime power systems, we never even accomplished that with, right? You got power converters if you travel the world. If you're traveling the world, Ethernet, whether you're here, whether you're in Tokyo, whether you're in Frankfurt, Ethernet's all the same. So it's truly a revolution in terms of what we can do. And that's driving a lot of what type of increases in capacity we can handle, but also what kind of overall network efficiencies that we can get. So we've got an architectural shift. We also have equipment change, right? And this is by benefit of the guys who build semiconductors have been driving tremendous improvements in processing capabilities, clock rates, the ability to have much higher density processing on a circuit. And this gives you a simple example, right? This is an example of a piece of telecom equipment that you would have bought back in the bubble days, kind of the 2000, 2001 timeframe, compared to something that's now is kind of the state-of-the-art product, something that would be generating, let's say, 100 gigabit kind of circuits and such. And you can see kind of almost a 40x improvement in terms of total capacity, total ability to process traffic on this sort of an infrastructure. And look at the type of power change that has gone with it, right? Again, a dramatic reduction in overall power consumption for a network processing element on a watts per bit kind of a basis, right? Processing far more traffic at every site, at every shelf, but overall the efficiency has gone up quite dramatically. And there are even examples, and it's captured in the bottom there, where a relatively small amount of network swap out, right, modernization improvement, can give you some really dramatic improvements in operating costs. Now, this isn't just power. It's power and sparing and complexity of operations, and are you doing things manually, or do you have an automatic provisioning system and such? But that is the kind of economic result that's needed to continue this to scale going out into the future. And photonics has a tremendous role to play. In fact, you can argue that when you start to move a network into more photonics, some pretty dramatic things can be accomplished. This was an example, very simple. This is a Latin American service provider. And to kind of scale things, a large network of national size in terms of US dollars consumed of energy might be in the $100 million class. A true global network, think the top 5 or 10 networks globally, would be approaching $1 billion a year spend on energy. Right? This is to operate the network, to cool the equipment, that sort of thing. We went through and just did some simple analysis. There was no architectural change. It's still the kind of ring-based architectures and such, but moving it towards Ethernet to OTN, just upgrading some of the key sites, saves a tremendous amount of space. In this case, we do it in terms of shipping containers because it's something people can typically digest. How big is a shipping container? How much of those did I save? And then almost 1,000 kilowatts worth of power reduction. And that's just prime power. If you factored in actual cooling and rectifier efficiencies on top of it, almost a 2x gain. And that was just touching a relatively small number of their sites, but key sites where they had a lot of traffic flow through and a lot of aggregation and such. So there's an ability to optimize between the photonic side and the electrical side. I can do, I can process a terabit electrically, I can process it optically. If I want to do it optically, I have to stay photonic. I can't do much with the bits, but it's very efficient from a power consumption point of view. I can process a terabit optically for kind of milliwatts to watts worth of prime power. If I want to do that electrically, I'm talking hundreds of watts to thousands of watts. Okay, and so it's that sort of a trade-off. And so when you're building any kind of a wide area network, and think of Ciena as kind of the company that kind of does the circulatory system for the internet, we like the fibers that go between continents, we like the fibers that go between cities. About half the cell towers in North America light up and come back into the network off of Ciena kit, so fiber going right out to the edge. You have a trade-off. You can trade off how much electrical processing to do, how much optical processing that I can do. And in the use cases here at the top, we're just showing, okay, optical wave switching only. Right? So I'm not going to go in and touch the bits, I'll just manipulate the wavelengths around. All the way down to electrical, where I can touch every photon-electron conversion at every location, to some sort of a hybrid where I can trade off how much do I do optically, how much do electrically. And what you'd like to do is have this kind of an optimum effect. Right? If I know my traffic pattern, I know how things are growing, I know what the connectivity and topology looks like, I can optimize the overall network, whether it's, again, wide area, metropolitan area, even large-scale local networks. I'm going to take you through now is just an example. This is an anonymized, but a good example of a USA nationwide core. So it represents what a large carrier would have in the States. 48 nodes, 61 links, about 1,000 protected connections. So we're using a protected topology here. We're going to explore a couple different dimensions. Okay, we're going to say on every one of these connections, what kind of traffic could be flowing. We'll do 1, 2, 10, 40 gigabits. And I'll use line rates. So this is the maximum rate on the line, and then each one of those is on a different color of 10, 40, and 100 gig. 100 gig is pretty much state-of-the-art for today. And the kind of unit of currency at the edge of the network, many of you heard, is kind of a gigabit. That will be moving to 10 gigabits over the next few years. So this is a pretty representative analysis of what this sort of a network would look like. And what I'm going to do is look at it, again, from kind of a pure optical point of view. And I'll just set up wavelengths wherever I can. And what I'm going to find out is I try to scale this network up. And the colors on here represent the number of wavelengths, and you can see the actual switch sites, if you will, the points where the network actually intersects. The height of that is effectively the complexity, cost, and power consumption of that particular location in the network. And so if I try to do it in terms of an all-optical architecture, what I'm going to find very quickly is I've got a lot of hot links. Not surprisingly, I'm burning up a lot of wavelengths, whether they're completely filled or not. I'm going to dedicate a wavelength because I have to get that connection. If I want to go ahead and do it with all electrical, and keep in mind, kind of as a soundbite, this is how the original internet was built. Okay, the original internet had the premise that all the connections in the network were scarce resources. They were hard to get. Remember, it was built in that old dial-up arena. And so I have to do a lot of processing to get efficient use of that. Well, what I'll see is, yes, I don't have a lot of wavelengths consumed, right? I'm not using a lot of my interconnecting capacity, but boy, I've got some very complicated, very hot, very expensive to operate switch locations. Okay, so obviously, can I optimize? And sure, the answer is yes. I can build networks where if I can optimize between how much I do on the photonics side, how much processing I do optically, wave switching and rerouting and bypass and those sorts of things, and how much I do electrically, which means I go through an OEO conversion, O to E, do some electrical processing, go E to O, then back out on the line. If I can optimize that, I can actually get a much better result. And it's some of these techniques that is what's going to allow us to continue to scale this network up, but not have it consume 10 and 100 times as much of the primary resources that we've got. So it's actually very interesting times to be in the networking space. I was talking to Rod earlier. Within the last probably 2 years, the kind of conversations that I have with the CXOs inside of the carriers has changed. They know power consumption, space, that is an issue for them. In fact, in some cases, what they're starting to say is, we're looking at capping the power in the network. We'll spend this much, but we're not going to spend anything more. Here's an envelope. Anything you guys have to do to make my network go faster, go further, have higher connections, you got to fit within this envelope. Right? And that's a forcing function back onto us as the system providers, and then back into the device and component and subsystem folks on how to actually build that. So when you look at kind of the toolbox that we've got today, right? Tools for power efficiency. We talked about the equipment upgrade, these architectural shifts that are underway with WAN 3.0, Ethernet OTN, convergence between packet and optical, where we don't have optical boxes and then you buy packet boxes on top of it. It's one box that does everything, everything from whites to fiber, that gives you all the packet structure that you need. The use of optical bypass, where I can optimize, moving from rings to mesh. Rings had 100% redundancy, sounds pretty inefficient. Mesh, much more efficient in terms of your operations. But now you look out into the future, right? What do we expect, or what we'd like to have into that, the toolbox in the future? The networks we build today are largely constant dissipation, right? They're sitting there humming along, dissipating energy, regardless of how much traffic's on them. Okay? We can start to make things that are variable dissipation, right? Be smart about how we're actually using the energy to light the network, to actually operate the network, right? Make things adapt to the amount of traffic that's flowing through it. There's great gains still to be had through greater integration. Silicon photonics, which really is, from my perspective, the next great thing in terms of integration. The ability to do all of the processing in silicon, I think, has got great benefits going forward. Getting away from having to have every laser in the network cooled, which consumes power and the rest of it. Getting to uncooled lasers has got some very interesting capabilities. There's a huge piece in here that I'm going to glance over, which is virtualization. We're very comfortable virtualizing our storage resources and our compute resources. We're not nearly as comfortable virtualizing network resources, and we need to get better at that. Right? There's a real opportunity for Connect, which is the network, compute, and store to come together to build a much better machine than we've had in the past. Right? And it's time for us to go do that. If you look at how to continue to grow, once we're up against things like Shannon's limit, parallel systems, parallel fibers, parallel amplifiers, all that has to play in there. And there's even now the discussions, and this is a bit of 10 years ago, this would have been heresy in a central office, water cooling. Right? There are some applications where water cooling really does make sense in terms of getting the equipment cooled, getting the heat out of the infrastructure and such. So again, I would tell you it's a very good time to be in the networking space. The toolbox is getting better month by month, year by year. The network matters like it hasn't in about a decade or so. So with that, I thank you and turn it over to next.
Well, thanks. It's a pleasure to be here, and who can't enjoy coming to Santa Barbara with the weather? So I'm going to talk about sort of, I was asked to talk about silicon photonics and why silicon photonics and what it's allowing us to do relative to changing the way we architect and design future data centers. So I'll first talk about trends in the data center. It's sort of the same thing, data. It's all about data and big data. I'll then talk about a key technology, which we've sort of bet our technology on, which is the hybrid silicon laser, which is actually something that was started here with the University of Santa Barbara. And then I'll briefly talk about this new photonic architecture, which we announced with Facebook, which shows how you put all these pieces together and what I think it's going to do for the future scaling of the data center. And then I'll list some challenges. So everyone sees these different plots differently, but if you go here from left to right, it's just showing different types of data that are being consumed today. And when you look at these numbers, they're somewhat astounding, and I just updated the social one this morning. But if you look at just a simple CT scan, it's a petabyte of data, right? So you take a CT scan, you have all this information, you have to move it. Social media today, if you look at just YouTube, if anybody could guess how many videos are looked at or downloaded per day on YouTube? Anybody take a guess? 3 billion and growing, okay, a day. So when you look at photos, video, music, it's greater than exabyte of data per day and growing exponentially. And then if you take the extreme case, which I think won't be very extreme soon, the Linear Halogen Collider and CERN, they run these experiments, they run 2 or 3 months, and they're collecting all this information, and they're just transporting terabits of results. One experiment is roughly 300 exabytes, and you have to move that information and store it somewhere. And so you have all these devices, all this information, all this data. The question is, how do you connect all these, and how do you move it efficiently so that you can get the data when you want it, wherever you're at? So I won't tell you whose data center this is. And I don't remember, one of my team found this picture. I don't know where it's from, but this is sort of what's happening in the data center today. It's called scale up and scale out. Right? Data centers are getting bigger. They're putting more and more rows of racks of computers, and you have to connect them together. And that connection is getting more complicated. But because of limitations in copper, you can only connect so many of them together, or you compress them. And so we're running into limitations, no longer at long haul, but within the 50 meters, the 20 meters. As you start aggregating and running more information, you're seeing limitations of how fast you can run these copper links, the power that these sending signals down a copper wire, and the distance over which those signals can transmit. As we move from really 10 gigabits per second to 25 gigabits per second, is sort of this next real evolution that's happening. And then so the question is, how do you distribute that efficiently, both from a hardware perspective and a software perspective? And so the question is, can low-cost photonics allow and help with scaling? And you have to understand, scaling is not just speed. One of the big benefits, and if you look at another interesting data point, pick your number, 35, 40, 45% of the cost of a data center in some way, shape, or form is cooling and thermals. And so just by separating things, just by eliminating the cables and going to thin fiber and allowing efficient cooling of the air that's flowing through the data center, that savings alone is significant for the data center, the total cost of ownership, independent of going faster. And so we've been working on silicon photonics. I've been working on this for almost a decade, or over a decade. And so we started with this, hey, if we can take the benefits of what we've done in the IC industry, scaling, integration, Moore's law, combine that silicon manufacturing with optical communications and the benefit of optics, the ability to go very far, very high speed over long distances, and more importantly, immunity to electromagnetic interference. And if we can combine those two and build these devices in volume on a silicon platform, and what we call drafting Moore's law, you now have the potential to put optics everywhere. And it's sort of similar to wireless, right? 10 years ago, you had to buy a card to put into your laptop. Today, you don't think about it. You have 3G, Wi-Fi, WiMAX. Can we get to a point where optical is a technology, and now you can start connecting things? And to do that, we believe if you can do it on a silicon platform, and you can draft this hundreds of billions of dollars of infrastructure, you have a way to drive optical to very high volume, and more importantly, to all the endpoints. So one of the key technologies, I call it a core technology, what we call the hybrid silicon laser. It's actually an activity we started with Professor Bowers. We were actually having dinner last night, sort of in 2004, 2005. I think those are good days, if I like a better words. It was a very exciting time. In 2006, we demonstrated that first technology. And think of this as this hybrid electric car, right? We have the ability to marry indium phosphide and use it as an emitter, combine that with silicon, and then the silicon actually does all the performance. So we have gratings in silicon, the indium phosphide is just a light emitter, but what we're able to do is get wafer level processing of lots of lasers with very good performance, and although even in John I couldn't tell him, we're getting it with very good yields, and we're producing this technology in a short amount of time, less than 6 years, with very high volume. And so it's an exciting piece because it addresses one of the key components of how do we put silicon or combine silicon and how do we get efficient light. And so by doing this hybrid approach, we're able to combine the two. And that leads us to, and this is something we talked about 2 years ago. We haven't publicly talked about our commercial product specifics, but what you see there is on the upper left is an actual silicon chip that has the hybrid silicon lasers processed on the same die as our modulators. And so we're basically, by having these chips, we can actually have a silicon chip that the lasers fire up, they get coupled right into the silicon, we attach a fiber, the silicon's put down on FR4 just like anything else, and now we're communicating between two pieces of silicon, and on the other side is a receiver that has silicon germanium that now can communicate optically instead of electrically. So we've eliminated all the bounds in terms of distance. We're able to do this much more efficiently because you don't have to drive these highly powered IOs over time as we optimize these. And what that allows us to do is start doing things like this. So we can take this network today that's this cluster of copper cables in a rack, and now we can start thinking about putting fiber up and down the rack. And so if we had the fiber, as I said earlier, it's not just bandwidth, it's the ability to open up. We have, and I know Sawagi's here, but we've been working with Corning, and we announced this as part of the announcement of Facebook, and not just taking fiber, but we've developed and designed a new cable, a new connector that's optimized for the data center. So it's optimized for low cost, it's optimized for scalability, so we can scale this cable and connector as we put more and more fiber within our racks. And so we now, I think, have an ability to put fiber and connectivity, but the real question is, that hasn't been the limit. The limit has been the optical modules. And so this is what we call a new architecture, or new photonic architecture, which basically takes an old technology or disaggregation, which has been around a long time, but if we could do things cost effectively, and what we're talking about here is bringing 100 gigabit per second. I know Steve talked about they've been using it in the network for a long time, but what I have here is a picture. Let me explain this. I've looked at this so often. That what you have on the lower right is a tray, typical tray in a data center rack. And what we're able to do is we separate the back side, which has the power and the fans, and what we call a mezzanine card, from the CPUs and memory. And we're able then to drop in there, because the photonics, and based on silicon photonics, are cost effective enough that we can put it into the tray. We have different scenarios where we can put an Ethernet-based switch where we actually aggregate PCI Express. So think about it, 9 channels or 12 channels of PCI Express at 8 gigabits per second, that's 90 gigabits per second. Our typical CPUs have 40 PCI slots, or PCI channels. So there's an enormous amount of bandwidth coming out of there, but here we're able to aggregate it. We can put it into a photonics module that sits in the back. We have a fiber that comes around the front, and then it connects up and down the rack. So because we can do this cost effectively, we're able to do two things. We're able to plumb essentially the system for future use. So you plumb it once. Andy Beckelsheim told me when we were talking, he says, no one's ever wanted a slower network, but no one wants to pay for the faster network. So the idea here is we can plumb this rack once with bandwidth that we can grow into, and over time, you can upgrade CPUs and memory independently. You don't have to change the infrastructure. And that is becoming a huge opportunity for the data centers to drive efficiency. So they can upgrade to more efficient processors, but they save overall cost because of the infrastructure stays the same. And so what are the challenges as we go forward? And I think some of these challenges, they're very philosophical, for lack of better words, but at the end of the day, it comes down to cost, all right? Copper, at the end of the day, it's pennies per pin. And so just good enough is the new mindset, both in the data center. And so you have to look at the total cost. And it's not just the silicon photonics, it's not just the hybrid laser, it's the module, it's the packaging, it's the connector and the cable. And that's why we've actually had to look at the whole solution so that we bring the entire solution out and not just one component. Power. This is a never-ending thing where it's always about power efficiency, milliwatts per gigabit. You have all these IOs, and these data centers are becoming more and more power hungry, so constantly driving the power efficiency. And this means optimizing. You're always going to pay something for the optics, but if I can optimize the two, then I can drive the electrical down and then bring an overall system. And this is a constant system-level challenge. Packaging, I put packaging size density. Real estate is very expensive on these boards. And so anything you're doing to reduce the size, reduce the packaging, and also what we have to do to drive this is change the packaging of the optical industry. These big modules with gold-plated boxes, you can shave the gold, but they're not going to be cheap. And so you need server-like assembly, server-like sockets, server-like plug-and-play, because that's what the industry is used to. And then lastly, it's thermals. And I say thermals differently. These CPUs and these systems and these ASICs and these switches consume a lot of power because they're running a lot of packets. And then I want to put my optics as close as possible to that. But how do I do that efficiently? And how do we get, today the standard is 0 to 70, but we want to run lasers at 80 degrees or 85 degrees or 90 degrees. And so there's a lot of materials work of looking at the material properties, whether it's quantum dots or others, to continue to drive not only the efficiency of the lasers up, but also make sure the efficiency of those lasers operate at very high temperature. So, thank you.
Thank you for having me here today. It's certainly a pleasure to be here. And I thought I would, so when I was asked to give this talk and Professor Bowers asked me, I asked him what I want to talk about, what do you want me to talk about? And he said, well, why don't you talk about the different types of data centers, the energy efficiency issues associated with them, how you might solve them, and the role of photonics. And I said, okay, how many slides do I have? So about 4. But so I will try to do that in about 4 slides, and but I will paint rather broad strokes. And so I must, as a preface to my talk, I apologize in advance if I use too broad a brush and I omit a lot of important details. And depending on how that goes as an epilogue to my talk, I might indulge in a quick hurdle and 30-yard dash to the door. But so to go on, the first slide, sort of what kinds of data centers? How would you typically differentiate data centers? And the conventional wisdom would say, well, there are many ways to do this, of course, and you have to, one way to do it might be to actually do it in terms of usage, whether you have a data center that's focused on scientific computing, whether you have a public cloud, perhaps, that's running search engines or social media. You might have private clouds where companies engage larger vendors to kind of have their own private cloud that can be accessed remotely, or perhaps just in-house data centers. So that would be conventional wisdom and how you might classify them. I will depart conventional wisdom today, and try to define data centers in terms of two axes. One of them is sort of how much compute power you've got, and the other is how much bandwidth you need. And I'm not going to, for the moment, differentiate between whether you need I/O bandwidth or inter-processor communication bandwidth or just memory access bandwidth. I'll leave that sort of hidden beneath the broad brushstrokes. But the first thing you realize is, well, there's actually two quadrants to this graph. One of them on the right-hand side is the floating point universe, which is really more scientific computing, and the other is integer. And I'll come back to the right-hand side, but that's sort of where you are building high-performance machines to deal with specific mathematical problems, and the amount of information that you transfer is highly dependent on the math and highly dependent on the the algorithms that either tightly couple or don't tightly couple the data within that mathematical framework. And so you see sort of data access go all the way up and down there, and we'll get back to that in specific examples. On the other side of the fence is sort of the integer applications. And what we're seeing there is that there's a lot more focus now, not only on the perhaps if you're a large internet search company, you'll be doing a lot of search queries on a Hadoop-style machine with a lot of scatter-gather programmings that will cause you to be in sort of the bottom of that cloud area. We're also seeing a lot more sort of data-intensive applications, where including, for example, online analytics, where it requires a lot of data access in order to complete the task, and we're seeing that sort of driving the high end of the access space, data access space. So going to specific numbers now on the next, I'm giving you two examples, both on the HPC side, and these are all both publicly available data, where you've got two machines. They're both petascale machines, and they both and they deliver. In the first one is sort of a commercial machine, the Hermit machine. The other is a Zinn machine, a Livermore machine that is the government machine. And they deliver at the end of the day about half a gigaflop per watt. Now, to put that into perspective as an industry, the first machines built, in the first computers built, did about 1,200, maybe 2,000 operations and consumed about 100 kilowatts to do that. Right? So these, and now the latest, the greenest machine on the planet, the Beacon machine, the University of Tennessee and Oak Ridge, does about 2.5 gigaflops per watt. So that's an improvement in the industry and a community of 11 orders of magnitude. So the question is, well, how do we get the next order of magnitude beyond this? And again, these examples here are really one that if you look at the numbers, provide only about a half a byte per second per floating point per second, so half a byte per flop. Right, and what the programmers really want is about 1 to 2 bytes. So this is already about 4 times less bandwidth than they want. So if you look at sort of how we're going to get that next level of 10, you have to actually not just look at the processor anymore, because that used to be the largest energy user in the system. But you have to look at 3 things. You have to look at the processor, which today at best maybe gives you 1 to 2 gigaflops per watt. You have to look at the memory. And I give an example of the Oracle buffer on board, very similar to the Intel scalable memory interface. And that consumes about 10 picojoules per bit to transfer the data to and from that DIMM. And then you have to look at all of the rest of the communications, is about 10 picojoules per bit also. And this is for tightly, systems that are within a rack or a few racks or within a small-sized data center. So how do we improve that? The first thing is to improve the processor, right? So to go from 1 to 2 gigaflops per watt to, say, perhaps 10x of that is actually something that's well within our capability now. We know now 2 techniques to do that. One of them is to build special purpose cores. So you don't try to use a core to do everything, but build cores that are specially suited to that task. So you're building heterogeneous processors. And secondly, turn it off when you're not using it. So those 2, again, broadly painted brushstrokes are going to give you that jump from 1 to 2 gigaflops per watt to 15 to 20 gigaflops per watt. Now, once you do that, you realize that the long pole in the tent is no longer the processor, but now the memory. So what will you do about the memory? So to improve memory energy, there's a lot of effort going on in terms of stacking memory. So the tricky part about memory is that it has to be very cheap, right? You pay only fractions of a penny per, maybe $1 for a billion transistors on a memory chip, but you pay 100 times that on a processor chip. So you have to be very price conscious, and so you can't change the DRAM. But some really good proposals we've heard, and systems are based on stacking memory and sort of compacting the system into a stacked memory die that can save you perhaps 50 to 70% of that energy. And then finally, that leaves the longest pole in the tent at the system level at the interconnect. And where we are at the interconnect is sort of between 10 and 20 milliwatts per gigabit, or about 10 to 20 picojoules per bit, in terms of transporting the energy required to transport bits across your machine. And that's basically a combination of the electrical drivers, the serializers, deserializers, and then the optical bandwidth between them. And that, we believe, using silicon photonics, as we heard recently before me, and perhaps some very innovative circuit designs and integration approaches, which I won't talk about here, but we are working very hard on at Oracle, will allow you to take that extra 10x out of the interconnect. So, but to get the optics in, energy is not the sole criterion. Deferring to what Rod Alferness said, it is a very important driver, but not the only driver. We have to look at reach, bandwidth. In fact, historically speaking, if you look at the penetration of optical links in systems, it's always been reach and bandwidth driven. But if you focus on the top right of those graphs, what you see is that as you get more cores on a processor, as you compact the memory system, the density of the interconnect also has to become comparable. So you're talking about tens of thousands of links and with very high density. So density and cost are certainly going to be very important drivers, in addition to the energy, distance, and bandwidth. And that is where we believe if you can get to a picojoule per bit using a silicon packaging technology, that will be what is needed for completing the triumvirate of low energy technologies for the data center. So in summary, must improve. You've heard already. Must improve. Must continue to improve the performance and energy efficiency of clusters and data centers. We think we have a roadmap for the next 10x reduction. We haven't talked about the details, but it will be forthcoming in a report coming out. But we think that a photonically interconnected system, particularly using silicon photonics, can be 6 to 10x more efficient than a comparable commodity data center in about 2018 to 2020.
Thank you, Ashok. I'd like to give my perspective on this. The Institute has run a couple of roundtables recently. In fact, I think each of them have had representatives of all these companies at those roundtables, and they're listed on the slide. We did one on data centers, and this is available on the website. And more recently, we did one on core networks, and that's just now being finished up and looking at all these issues we've been hearing today. So this is the same version or different version of what Mario and Steve showed, but this is the driver for our industry, the increasing amounts of data that need to be transmitted. So there's a good economic driver for this, obviously, but also this is the need now to make the efficiency of this data transmission far more efficient than it is. Fortunately, photonics is on a very good path to continually reduce the amount of power or energy required to transmit data. One metric which is particularly easy to measure is the amount of energy it takes to get a bit across the ocean. You can do a similar curve within a data center or for Steve Alexander's case, across the country. But what this shows is a reduction of factor of 10 to the 12 in the amount of energy it takes to get the energy a bit across the ocean. And so that's the good news. Those curves in the lower right there where it says 1000x, those are the photonic cables across the ocean. And we have seen in just a shorter period of time, 30 years, a reduction of a factor of 1,000 in the amount of power it takes. As a result of a lot of these innovations, some of which Steve talked about, optical amplifiers as an example. The issue is, how do we stay in this curve in the future and continue this improvement? Within the data center, there is an architectural change that applies to both what Mario talked about, silicon photonics, but also in terms of switching. So on the left, that's a classic architecture that data centers today use. It's a multi-tiered architecture, highly oversubscribed, which makes it relatively inefficient, but you're limited by the connections through there. And then on the right-hand side is where things are moving to, which is a much tighter, laterally connected, east-west connected rather than north-south connected. And the problem with that is it requires much larger switching elements when you interconnect these, and takes much more power with today's technology. And the question is, how do you solve that? And one solution is the same in the data center as it is in what Steve talked about, which is to switch things optically. And this makes tremendous sense. If you think about sending a movie or one of Mario's many downloads on YouTube, it doesn't make any sense to break that into packets of a few hundred bits or bytes and send all those packets across, and at every router across the country, look at where that destination should be. You need the whole movie. So just compress it to a high data rate and send that entire movie with one header on it. And you can do that with circuit switches. It's going to take you milliseconds of time to transmit a movie or a book or a download. And what this slide shows is the work of a company in town, Kelly Networks, which is a partner of the Institute. And by switching things optically, it takes far less power. So the green bar there with the arrow underneath it is what a typical power is to, say a nanojoule per bit to switch in a core router. And the far left-hand side there is what it takes to do this with MEMS. And again, it's an all circuit switched approach. The advantage of MEMS, you can make large switches that have 300 ports in them and carry literally, hundreds of terabits of data at a very, very highly efficient rate. Many orders of magnitude more efficient than what we have today. And what's shown on the right there is what architecture looks like, and you can see there on the lower right a picture of what a MEMS chip looks like. So again, this is done with silicon, high volume manufacturing, and at high yield, and that's a good solution for data centers as well as for long distance communication. For the transmission portion now, that was the switching, for the transmission portion, you get into issues as shown in this plot. And that shows the evolution over time of increasing data rates. And if you look at that lower one, the serial interfaces shows the 100 gigabit standard that was adopted a few years ago and is in production and widely used today in networks. And then next to that is an arrow with a question mark. That actually has now been decided. The next standard after 100 gigabit will be 400 gigabit. And the standards committees are meeting, determining what those standards will be. And that's absolutely essential to our industry to be able to plan, to meet, to have standards to get everyone working in the same direction. The upper curve there, the one labeled WDM, is the aggregate capacity down a fiber optic cable, and it's getting very large. It's on the order of a terabit, 10 terabits per second, but indeed we've seen a need to get ever higher. And the ways to do that are shown in this slide. So at the top there, it talks about all the things that we can do. So time means going to higher data rates. That's limited by electronics, but certainly largely 10 gigabit today, 25 gigabit, soon higher data rates of clock speeds. Polarization means combining the two polarizations. That doubles the data rate you can put down the fiber. Frequency refers to putting multiple colors of light, and that's certainly done today, upwards of 40 colors or more. Quadrature refers to using coherent communications, and that starts to become very interesting. That's what the array of blue dots on the right-hand side is adjusting the amplitude and phase of the light. So you don't just turn it on and off, but rather you have some multi-level coding like you would in a cell phone system. And the end result of all this is we can get much higher data rates by combining all of these things. But now the optical devices become very complex. So Mario showed the first step along that path of having, say, 4 lasers combined with 4 modulators and a combiner. But now we need something actually much more complex. We need polarization combiners, we need coherent transmitters and receivers, and we need all these different, replicated all these different colors put together. So the theme of this, and the theme of what I want to say today, is it is all about integration. And so you have lots of transmitters integrated together. You don't have separate line cards. Lots of amplifiers integrated together. That's the blue or the red curve. And lots of receivers integrated together. And then the bottom one in the center is the final level of where the world is going very, very rapidly, is to have multiple cores in the fiber. So Mario showed a very nice cable that had 24 fibers in it. In the future, those 24 fibers might each have, and this is what's shown there, 7 or more cores inside of that. So again, that's another level of increased capacity from where we are today. And that, if you're going to have one fiber with all of those cores close together, all of those receivers and transmitters obviously must be integrated together on a single chip. So it's just driving integration is the whole key. So our focus has been what we call hybrid silicon integration, using a silicon substrate. Silicon is a tremendously inefficient emitter. Its emission efficiency is 10 to the minus 6. It's like one of the worst materials you could use. But by putting 3 5s in there, like indium phosphide or gallium arsenide quantum dots are very interesting. One can get light emission, absorption, modulation on there. We also work in other aspects. The lower right corner shows magnetic materials. Bonding magnetic materials on there allows us to integrate isolators and circulators along with these active elements. And then the 2 in the center are very important, and increasingly. So today, you have typically single chips, but going forward, we're going to have multiple photonic and electronic chips, processor chips integrated together, all communicating optically with each other. And then you start needing to have a platform to do that. Our focus has been using silicon dioxide or silicon nitride waveguides, and we can get roughly 1,000 times lower loss in those than can in either indium phosphide or silicon. And by processing these on large area wafers, you can now imagine having very loss interconnections between lots of processors and memory all within one of these cards. So that's very much where we're headed. Our goal is increased levels of integration, and unfortunately, we're incredibly primitive compared to electronics. So where we stand is shown in this slide. The blue dots are the best that's been done in the optoelectronics industry, predominantly based on indium phosphide results. And there's a UCSB dot there. That's some work out of Larry Calder and Dan Blumenthal's group. Infinera, I think, has the highest level of integration of any photonic chip shown there. The red curves, though, are what's been done with silicon. And it appears at this point to be a more rapid evolution. And I think actually it truly is, because the process control that places like Intel have on these devices is phenomenal. It's kind of unbelievable to me. And so your ability to make devices in high yield with very high precision is phenomenal. The last red dot there is not done. That's the chip we have in fab right now, so we hope this does continue, but it remains to be seen. Around the outside are some of the chips that we've made at UCSB, so things like QPSK receivers, optical scanning beams, the lower right, digital tunable lasers in the bottom. The lower left is an optical buffer chip that we made in collaboration with Cisco. So just an example of what we need to do. But again, the numbers there, and those are numbers of devices per waveguide. So a chip might have multiple waveguides on there, like those 7 fiber chips would have 7 times this, say. But we're on the order of a few hundred, 500 chips integrated together, 500 devices integrated together on a single waveguide. But increasingly in the future, as we get more complex transmitters and receivers, that's going to go to tens of thousands. So I think the future is very bright. And the advantage of integration is that you get lower loss between all of these, which means much less power and much higher performance. So it is an efficiency play in the end. So with that, I'll quit.
Okay, thank you very much. So I guess I would just make a couple of comments. One is hopefully the message that you heard, or that I think I heard, was that in general for transmission, optics is the energy efficient way of doing things. And so So very often, the question is, can we build it at low enough cost to replace what's currently there, which is typically copper. So that's the push towards being able to justify in a cost-effective way optics as the interconnection distance gets shorter and shorter, and integration is a key way of doing that. I think on the long-haul side, we have already seen that optics drives down the cost per bit as long as the demand continues to go up, right? So you can aggregate all that on one fiber. And now that's beginning to be our issue, because the question is, can we continue to grow that number by a factor of 100 over the next 10 years? So Steve, let me ask you that question. So are we going to be able to continue to drive down or drive up the efficiency by continuing to get more bits on that fiber?
So I think there is probably 3 to 6 dB to be had, right? So 2 to 4, we think we're there. The biggest issue really is the passband of erbium, right? So the fiber itself is actually much broader bandwidth than our ability to optically amplify. So I think there's been, kind of two vectors established. One is, can we do something with other amplifier technologies? And Raman's one, semiconductors are another. There's other dopants and such people are looking at. And the other one is what was covered, which is really parallelization of the fiber itself. So we have this kind of 50 terabit or so limitation for what we currently understand how to do with erbium. Maybe we can double that with being smart about some things, but we are up against some limitations.
And then on the other end, in terms of driving down to shorter and shorter distances, and the trade-offs there, and clearly there's a timeline, but how short can we go, right? How far into equipment, not just for what we now consider as interconnect kind of between racks, but as we carry this down to the chip-to-chip level, is there a sense of what that time frame will be and what those distances might be?
We shouldn't look at this as where's or when's it going to get into the chip-to-chip, because I think one thing you have to understand is make sure we're applying the right technology to the right problem. And Moore's law will continue, and so as you throw more and more transistors at it, you actually start seeing in the 6, 12, 18 inches that the electronics continues to come up with things. And so you really have to make sure you apply the optics for the right applications. It's starting in the data center, it's at rack to rack. Hopefully we'll start bringing it into the rack. I think we're a long ways away from chip to chip. I mean, because you can do quite a bit with copper, but maybe Ashok.
I think it's from a performance perspective, I think the performance of the devices are already kind of there. Then the question really is one of cost, volume, penetration. We think that in terms of getting it into the rack, I think next generation of systems will have that. And I think the prices will be, as you said in the chart, about maybe getting down to $1 per gigabit per second of transport over distances and anywhere from 1 meter and above. Your second question is a little tougher, which is how do we get, perhaps replace wires on a printed circuit board, and that's where costs become, pennies per gigabit per second. And even with the volume and the manufacturing advances that we've heard today and available with silicon, there's still the laser, and there's still the packaging, and that's a harder, I think, to anticipate exactly when that will happen.
Let me ask one more question, then we'll open it up for questions from the audience. And in at least one of the other sessions today, and probably more, this question about how to bring together industry, government agency, university partnerships to drive forward in some of these, in particular in these areas where energy efficiency is critical to kind of get to the next step. Your thoughts on that? Are we doing enough of that? Do we have enough do we have examples where that's working? Could that increase the rate at which we have success in this space?
Well, it's certainly, the problem obviously is that very few companies can build these $7 or $10 billion fabs for the most advanced CMOS. And so So the electronics industry has already seen the need for shared processing, and the photonics industry doesn't really have that yet, right? So pretty much everyone makes their own devices in their individual fabs, and there's a little bit that's happening, OPSIS being the first example. But yeah, I think there's a huge need for that, and I think very soon universities will need to very much rely upon much more advanced fabs than we have. So in many cases for our stuff, we used, in our collaboration with Intel, they did all the silicon fab, and they made very nice, all the lithography DFB arrays, and then we did the backside processing on that at UCSB, and they worked out very well. So I'm hoping that general model can continue. But on a national level, I think it would be great if we had a national photonics initiative for manufacturing. Would be, I think, very important.
Yeah, I think some of it may be, we still tend to operate in industry silos. So what we're doing, can again, think of where we are as kind of this wireless towers back into the network and then across continents, right? The volumes in that space, while large, are nowhere near what you're going to get in an interconnect space. So you'd like to leverage a lot of what they're learning on how to do, the chip-to-chip and, rack-to-rack and bay-to-bay interconnects. And yes, we'll need some somewhat subtle differences to make it go longer distance, but the basic building block, the basic platform, if we can get some commonality there, that can drive some very interesting results, right? We can't have the world be where it's $10 for me to connect from me to the wall and then $10,000 to get across the town, right? That doesn't make any sense. And that's unfortunately the way the world has kind of grown up in some senses, these industry silos.
Okay, thank you. From the audience.
Thank you. It was excellent presentations. I think the part of the cost question is not only about the cost of building photonic devices, not only the cost of building LEDs, etc., but also electricity price, the energy price. And we all agree that we would like to promote efficient technologies. At the same time, we have one of the lowest electricity price in the United States, the lowest water price in the United States, and at the same time, we hope that these efficient technologies are promoted in the United States. I think it's very difficult. So, for instance, Germany, they pay about twice more price on electricity as we do, and we use, not surprisingly, twice more electricity per household in the United States as compared to Germany. So I see that the question of promoting efficient technologies needs a kind of concerted action among different disciplines and parties, not only from the technology side, but also policy side, and education, awareness improvement, etc. And how we should bring all these pieces together to really bring these efficient technologies on the market, and what is your thought about that?
I think the biggest way to get real increases in efficiency is through integration. That was obviously my talk. But I push back to Steve, for example. I think this may not be true any longer, but certainly photonics always used to be based on 50-ohm technology, and electronics was far enough away from the photonics that you drove it over a 50-ohm line. I don't know if that's still true or not, but
it is in some cases, right? And that we know is inefficient in a lot of ways, right?
So
getting levels of integration up is a huge benefit.
The comparison is this iPhone, if the transistors were connected with 50-ohm lines, would take a megawatt of power to do what this does. And so the real advantage in integration and getting the electronics and photonics together is eliminating that, and it's orders and orders of magnitude more efficient. So to me, that's the best way to make a dramatic improvement. And we're just starting. I mean, we're just beginning that.
There's from the communications space in general, there are some, touches a lot of other things, right? It touches, as we heard about earlier, virtual travel and such. If anybody has used telepresence sorts of systems, they are remarkably good. You do have to kind of change behavior a little bit to just think about that sort of an environment to conduct a meeting in and such, but that addresses, reduces travel budgets, reduces fuel costs. I mean, you can use communications to offset costs elsewhere. And what I think is missing in some sense is, call it a national policy, if you will, to facilitate that sort of an environment. Right? We do know, and if you pay attention to what goes on overseas, there are other countries that have national initiatives around broadband service delivery. Right? And there are countries who have said, we believe it's competitive advantage to have every house fibered for this type of purpose. There are countries who are saying we want to be, the Swiss bank equivalent for data. Okay, so we're going to put data centers in our country, and we're going to have laws that regulate who can get to it. Right? So people are establishing positions on a national level in the cloud, access to the cloud, connectivity, bandwidth, consumption, all that. And those have some pretty dramatic implications in the overall energy picture.
May I also add then, to what John said earlier, which is that if you look at the total cost and the large reason to change technologies, it's power, yes, but it's also size and weight. Yeah. And data center floor space is one of the most precious commodities for many of the customers there. And so any technology that allows you to compact the system without having a quantum increase in your thermal load or your ability to, or requiring a new thermal technology will be absolutely welcomed from that perspective. So therefore, another aspect of the photonics is if you can get the interfaces dense enough, then you can compact your system and save size and weight, and that will allow you to save a lot of.
Yeah, so I think the point, at least in the telecom industry, is up until now, that may be changing. The cost of electricity for those networks has not been a driver. It has not. The issue has been cost of size and et cetera, and cooling in the switching centers, but not the cost of electricity. That changes in data centers because you've done so much aggregation. And again, I think it's beginning to be felt in telecom. Steve, you were commenting.
Ron's absolutely right. Within the last few years, the conversations have changed. 5 years ago, I would have never had an energy consumption conversation with a customer. Now, it's in the top 3 or 4 things people talk about. And there is this general trend, right? Central offices are the places that people aggregate inside of a telecom infrastructure. Well, central offices of today will be data centers tomorrow. Right. Okay, so if you look at how this world is migrating, telecom, datacom, computer, that's all kind of converging in a lot of ways. So they're going to face these exact same set of challenges. When they want to offer cloud-based services and you want to stream video and you want all that kind of high-def interaction, coming through what used to be called a central office, now with all this processing and storage, they're going to have the exact same set of issues. They know it, and they want to get ahead of it.
Dave, question.
Yes, I have a question about data centers and big data. And this may be naive because I don't work in the field, and you'll tell me right away if it is. But it strikes me that not all data is equal. That is, if we're talking about live streaming of movies or the kinds of data that an online marketer is accumulating, or perhaps a government agency for security reasons, is different in terms of not only the need to access that data, but the question of archiving it and things of all that sort. So my question is, if you're talking about the architecture of designing a data center, do you apply, is it one size fits all? Does an Amazon versus a Netflix versus an NSA, is it all the same, or are you actually taking that into consideration? And when you talk about different architectures and issues of energy efficiency and et cetera?
They're all different. So
they're all the same. Is that the answer?
They're all different.
They're all different.
They're all different. So if you take, just to give you an example, take a Facebook, for example, and you compare Google, right? Facebook takes an enormous amount of data, but people post photos, and in the first couple of days, a lot of people look at them, and then they don't look at them anymore. But what does Facebook have to do? They have to store those photos forever, so they have to figure out what they call cold storage. So they have a bunch of SSDs and stuff that they put in, they're looking at putting in a different building because they don't need that type of performance. Where someone like Google, who's doing search, who has to have access to the stuff right away, is moving. So they're starting, there is no one size fits all. And what the data centers are trying, each of these in themselves are trying to do is how do they find efficiencies? Because they want to try to maximize their volumes. And so they want to, this is where this disaggregation, ability to compartmentalize these things and reuse them, but connect them up differently, makes a huge difference.
In terms of the architecture and the issues that you're talking about here in terms of the basic technology, is it the same or do you approach it differently?
Well, we provide solutions. I mean, from Intel's perspective, and a lot of these data centers now, they're big enough that they actually do their own systems now. They buy the components and they design them themselves, and so they're no longer buying full systems with software. They're actually optimizing everything themselves. So they buy all the components. They don't need this. Don't need 2 power supplies. They strip it off, and they do their own things because it's just good enough. And they own both ends, and so they're designing and stripping their own systems individually to optimize for price performance. I don't know if you have something.
Right. So if you, and I tried to just do one segmentation of, how much of compute power versus interconnect, but you can, and then that's scattered all over the place, right? That's plot. But if you look at any other plot, and you can categorize it by the type of storage you use, it'll be all over the place. The amount of virtualization that you do in the data center, that will be all over the place. And it really is fundamentally, every data center is different, and particularly the applications that you pointed out. One of them was scientific computation. Again, a different type of data center architecture, a different type of compute a unit architecture as well. And so it's very different. One of the challenging aspects is really how do you get a data center that's maybe optimized for things like transaction processing, or lots of queries coming from outside, to also solve problems of analytics, where you actually have to not just send data to a particular user, but that user wants to know about maybe how the system is behaving, a business intelligence question, where you have to look at all of the data aggregated across all of the machines. And so even within the private clouds or the individual data centers, you find different styles of machines associated with different types of applications and queries that a single customer might actually request. You might have a customer saying, I want some of my employees to be able to access perhaps a set of files, whereas another set of employees of the same organization be able to query across and see what are the other guys doing, and give me some intelligence about over revenue versus product over a period of time. So again, even within the data center, there's different architectures to solve different problems.
Thank you.
Where latency is incredibly important, and if you can save 10 milliseconds in some process, it gives you huge financial advantage. So in that case, the kind of copper rack switch you'd have, latency matters much more than anything else, and maybe even want to use hollow core fiber because it's slightly faster than conventional fiber. It gets very crazy.
Putting microwaves just back up to just get rid of the slight delay from the index refraction of glass, right? I mean, that's somewhat of a latency-focused initiative, I would say.
Thank you.
Olivier, question.
It's been great listening to you guys. I've noted some fascinating numbers. I think, Steve, you mentioned in 10 years a factor of 38 improvement in energy efficiency. Ashok, from the first computer to the HPC systems today, 11 orders of magnitude improvement. So my first question is, that seems to be on the operation of the systems. Could you comment on the energy efficiency of the production of the systems? And that's related to the question from Sunnywood to talk about the total life assessment.
I'm sorry, could you just repeat the question?
The energy efficiency of the production of those systems, as opposed to only the operation side.
Okay.
So the actual manufacturing process.
Yes,
The manufacturer, the total cost in energy
Yes.
to build the network.
Yeah.
Good question.
I would probably say not well understood. Would be a good way to summarize it. I mean, we are keenly aware of certain pieces of it because it does turn into a cost at some point, right? But I think some of it is just the way, in particular, our supply chain works, from raw materials through component vendors to subsystem vendors, and we're a bit unusual in the sense that we're actually NAFTA based. In other words, our final assembly is all North American centric for some reason. But I'm not sure we have a good handle on total cost from raw materials for.
I also do not have any any concrete way of answering your question. The only stab I might take is that if you look at the cost of the system over time, they're about the same.
It's probably the same.
They're probably the same. So therefore, that means that if you equate cost with price, perhaps, or with energy, derated with perhaps appropriately, then that's the same improvement in the ability to integrate them. That would be my only stab.
The ICT, I'm sorry, go ahead.
It wasn't that long ago, I would say less than 10 years ago, in one of Ciena systems, say, every laser, every detector, every modulator was in a separate box. And the energy costs of producing those boxes and packaging those, I think, was considerable. Now you have, say, 40 lasers and modulators, detectors all integrated in a single chip, and there's a single connector associated with that. So Mario showed 24 fiber connectors versus having before that replaces probably 24 times 6 or 8 connectors. And so I think there is a significant improvement.
The efficiency is improved both at the manufacturing, the assembly, and the integration. The performance you're getting is going up orders of magnitude. And the nominal cost, when we look at, if you look at the data centers, the traffic is going up exponentially. If the cost to support that doesn't go down exponentially, you can't stay in business. So I think the costs are coming down very fast. I don't know how to quantify it.
I have a second and last question. It seems that the ICT industry, in terms of energy efficiency improvement, is kind of the first in this class. Improvements of 50% per year of that nature. It's very different in other industries like transportation, lighting, or energy. To broaden the discussion, how can the ICT sector help the other industries accelerate improvements in energy efficiency?
So is this a replacement question? Can we use the network to replace, or is it learnings from what we've done in the optical communication to apply to other industries?
To put things in perspective, the weight of the ICT industry in the energy footprint is about 2 to 3%, has been pretty stable. Lighting is 20%, buildings 20%, transportation. How can the networks help the other industries, big data or other secret sauce that you might share with the other industries to move faster?
I could offer a comment, and it's not an optimistic one. And that is, if you look at optical communications in particular, which is what we're talking about here, and you look at that energy per bit going down as you scale, right, to higher, as you drive down the cost per bit, the way you're getting that is because you're putting it all on one fiber, and you're using devices like optical amplifiers, which simultaneously provide amplification for all of those wavelengths, and therefore it's the aggregation of that which you're operating on that allows you to get the energy efficiency and energy per bit reduction. If you go out to the edge of the network, right, at the distribution network and to that line that goes into your home, that's also benefiting a little bit by this, but no way near the same as in the aggregated part of the network. If you look at the other examples, like lighting, it's fundamentally an endpoint kind of application, right? You don't get the benefit of aggregation in terms of as you do in the network. So some of what we've learned from networks apply only to network kinds of applications. But then there are things like the amplifier, right, which is just this wonderful thing of nature that if we could find similar materials for some of these other areas, then there may be some potential benefits. Other comments?
There may be an angle that smart grid technologies and such or rely on communications networks to control the power grid and such, right? But so those are examples where networking technology will help overall energy consumption. But I'm not sure, to Rod's point, I'm not sure there's direct parallels because we're leveraging off, quite honestly, a lot of what is done just in basic semiconductor processing. Right. The reason we can do coherent systems today, yes, there were improvements in the photonic side, but realistically what happened is the silicon got good enough that we could do 25, 30 gigasamples, A to D converters and processing at teraflop rates. And all of a sudden, once that happened, then we could delete a lot of the complexity out of the photonic system, right? So really the silicon caught up with processing speeds that we were doing really in kind of an analog sense in the optics. So we're all beneficiaries of the investments in the semiconductor technology.
I think, transportation was interesting. In my head, there's no way to aggregate 5 flights and put those people on one plane to get the cost down of that travel, or there's the gas that you have to spend. But I do think, if you can look at what are the key costs, I mean, we heard earlier that, the biggest piece of the cost for a flight is gasoline still. So I think as you move to electric cars and the batteries improve, then you can start really optimizing things with smart intelligence combined with communication to maybe optimize the traffic flow and reduce costs that way, but you still can't put 5 cars together into one. So I think there's some places where I just think, transportation is probably the hardest one, where I don't know, I think you can improve efficiencies, but the biggest one is, make cars lighter and make them more efficient, or not be so dependent upon gasoline. I think those are different types of, and technology I think can help there, right? Simulations and computers and other things can really accelerate, and or new materials, right? These carbon fibers and other things to drive performance and cost from a different, from lightweight materials that are very structured and high performance. So.
But again, I think to use the network to be able to, as a replacement basically, is a big opportunity, a huge opportunity.
In silicon photonics, we're using everything in CMOS, right? We're applying everything that people have developed in these advanced CMOS labs to make photonic devices. That's what lighting's doing, right? You're not winding filaments of wires, or you're winding compressed, compact fluorescent tubes and glass anymore. You're using old CMOS facilities, right? They're buying old CMOS equipment at discount prices. So, I mean, just like silicon photonics is following the CMOS industry, lighting's definitely doing the same thing. And they're going to get increased levels of integration eventually, particularly when they have, 3-color LEDs on a die, then you'll see it in space.
I think we have time for one last question. Please.
Thank you. Shifting gears a little bit, other than just energy efficiency of the network itself, there's the efficiency of the users who use it, and if the network goes down, the cloud evaporates, then we may, we're kind of out of work for a while. I mean, there's nothing we can do locally when our network goes down. Now, if we're dependent upon it to be doing our computing needs, then there's another element of, besides the local level now, there's the system level nodes and all that sort of thing could be vulnerable. I see a lot of improvement in reliability if you look at the shorter cables, fewer connections, and but on the other side of the basis of this photonics technology, will that, do you think, enhance the reliability of the network, as well as, which makes things more efficient and less energy usage from downtime?
I think the photonics plus the architectural changes that are in the works has already improved network performance, network availability and such. Your point around when there is a failure, there's still pain to be felt by the user community is well taken, but more and more of the networks are multiply connected. You yourself may have been to touch multiple networks just walking through this building and such, right? So getting high availability is both a technology base, and the silicon technologies, the photonic technologies have proven themselves to be very reliable, right? The basic component technologies is quite good. Usually what fails is a connector or an interconnection or those sorts of things. And then there's architecturally, have you provided what effectively looks like redundancy, right? You have multiple ways to get your mission accomplished through multiple types of touches onto the network. It gets to be pretty important. And that's a huge focus of the edge of the network, how it scales out, right? The grand internet kind of scales 2 ways. Photonically is what it uses, the photonic technologies are what it uses to scale capacity. Right? That's how we got from gigabits to terabits. The edge of the network, assuming it's just wireless for now, right? It's an antenna density problem, fundamental. The wireless technologies and how many antennas you have is what scales. And so what you want are lots of antennas, lots of things you can talk to. You want those things to be multiply connected back into the greater core. If you do that architecturally, then you can build a very reliable network.
And then related to that, our current solar cycles kind of not been so maximum as they thought. But, you know, I was anticipating there might be some solar flare directed our direction from the sun to the earth. And you know, there's talk about the fear of disruption of our power and perhaps our communication networks. And I was wondering if the photonics may make that more resistant to that sort of natural interruption.
At the end of the day, you can have virtualization, you can have redundancy. Stuff is not just stored on one machine now, it's stored in multiple places. But if you lose power, you lose power. I don't think that, I think that's the bigger one, right? I don't think that, so, I think they are more reliable. I think they're reliable because of the virtualization and because the stuff can be stored. Even when they're down, they're not down as long, right? I mean, now in the data center at least, you don't worry about if a rack goes down. You just unplug it and the next one takes over, right? Or at nighttime, you know, depending on, now what happens is certain systems are running during the daytime and then they distribute that horsepower at different places, East Coast to West Coast, and they'll put some of the information on the East Coast in the evenings here where we're still using it, but the East Coast is shut down. So I think the flexibility and the capability has improved it. I do think when there's a brownage or a power outage, I don't know how to, unless you have big batteries.
Both of your questions is, if you think about the network as really two different beasts, one of them is sort of the client to server, you know, where you really want, you know, dedicated bandwidth, guaranteed service. And that's one part of the equation, but the other side is sort of this peer-to-peer network where you want it ad hoc, as high bandwidth as possible. You know, availability is not guaranteed, but I think if you have the proper combination of both, and you think of the network as a combination of these two things, then it will I think redress all of the concerns. And you have to obviously scale up both networks and think about both networks as really your way of living, working, and communicating.
Okay. I'd like to take this opportunity to thank the panelists for their talks and the audience for the questions. And